G-Man, 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 it is good to hear from you, buddy. Haven't heard from you in a while. I've been stuck with fun people, and it's good to see you. It's good to see you come back. I was waiting for that New Year's video. I completely actually forgot about that. Then I saw it today. I was excited. And I have to say, I am impressed. I had a feeling that you would have learned a little bit, and I was absolutely correct. I had a feeling, if nothing else, you'd do it just to spite us for laughing at you. So, for that, I have to say kudos. And so now I want to try and answer the questions for you the best I can. Because there were some things I was like, dang it, he's so close. He's almost got it to understanding the science. Just almost there. But I'm glad you're making that video, and that you're wanting some answers. So, let us begin. A real, very simple layman's definition to this, because that's what I needed it to be. Basically, when it comes to our universe, we can study gravity, space-time, and light, and stuff like that. A singularity is, kind of by definition, any point in which all that goes to shit. Basically, because of the black hole pull, gravity was so tight that light can't escape, and light's jacked up, and space-time gets distorted. Because of that distortion, we can no longer do the math, and we're just, that's why we can't see inside of a black hole or understand really what's going on inside of it, because we can't observe it, and it's too much. We just have nothing yet. We have not reached that technological capabilities to be able to see what's going on. All right, G-Man, it's going to be time to break out the notebook, because this is going to be a little tough, because it really is a tough thing to try and break down. And beyond this, it goes over my head. So, all right. So, let's just go with a singularity. All right, let's say a black hole. In the center of a black hole, density is infinite. Now, why is that infinite? Density, the definition for it is mass divided by volume. So basically, when things get sucked into a black hole, they get compressed really ridiculously far. So it's basically now, instead of being like a mass, if you threw a bat into the black hole, it would just basically just get ripped apart right back into being, electrons and quarks. Now, an electron is fucking ridiculously small. It has a mass on an average of about, again, you may want to write this down, 9 to the negative 27th grams, or 9 to the 27th power grams. So that's, or 28 grams, or 0 with 27 zeros and then a 9 grams. Really, 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 really tiny. Now, that's your mass. What about the volume? Now, an electron doesn't necessarily, it's called a non-volume, or non-zero volume. But the thing is an electron moves, because it's moving around the nucleus, right? It moves like a wave. So it doesn't necessarily have a volume. It's actually, the electron, they did an experiment where they fired an electron out of a cannon, and they shot it through a double slit. It's called the double slit experiment. If you want to look, it's actually, double slit experiment, Professor Quantum or something like that. It does this really cool animated thing, and it shows you what they're talking about. But basically, the electron, as it moves, it forms a wave, basically by splitting and then coming back, and when that comes back, it forms into a wave motion. And literally, it can be 2 points at one time. Now, scientists, in quantum physics, are having a freaking ridiculously hard time finding them, because there's no way to know which way that it's going to split and what pattern it's going to split. It's just so freaking random. It's ridiculous. So, and basically, because it's a wave, it doesn't have any volume. So basically, you have a mass divided by 0. And when you divide anything by 0, you get infinity. So density is infinite. So what is inside? What does it look inside of a singularity? Don't know. It's just, can't tell. Like in a black hole, we can't see inside of a black hole because, well, light gets absorbed and we need light to be able to see inside. And we don't have any technology that can see inside of it. So it's literally, it's not, say, theoretical, but I guess so. It's non-physical at that point. I don't know. That's kind of a, I don't know. That's probably over my head. I'm really just talking out of my ass there. But it's just literally a point where everything is broken down so hard that we can't see it anymore. So yeah, I hope that answers your question, but we just don't know. Your next question, G-Man, was where does energy/matter come from? Well, basically, G-Man, energy and matter are like God. It's just always been there. First law of thermodynamics says that energy can change from one shape to another, but it cannot be created or destroyed. Energy is capable of turning into matter and vice versa. So, for example, like in the black hole, when something becomes into a singularity, we had matter, and mass, things with mass, was able to turn into energy. But it was not created or destroyed, it was just basically rearranged, basically into its physical, into electrons and protons, and all the, well, not protons, but electrons and quarks. So basically, yeah, it's always been around. Your next question was how does hydrogen basically turn into everything else? We consider hydrogen a base kind of element that we use to form everything. So how does it do it? Let me kind of back up for a second and kind of you have to basically kind of understand about the formation of stars and everything to really understand how this happens. So I'm going to try and give the basic version of it as basically as from what I can describe from it. Let's imagine you have a nuke, okay? Nuke goes off and heat and energy and particles and just everything's going everywhere, right? Okay, that nuke, its mass it's going because it's all this stuff's everywhere. But let's imagine, let's say we had a sealed container somehow and we could seal everything in. We set that nuke off inside, and all the heat would try to bounce out, but it couldn't. So it was stayed contained in that container. Basically, its mass stays exactly the same, which is that first law of thermodynamics. Matter can change from one form to another, but it cannot be created nor destroyed. You'll have to forgive the really bad editing that's going to occur because I've been coughing like crazy. So, yeah, if it's not as up to par with my usual excellent quality, forgive me. And that's why. Alright, so we have ourselves the Big Bang. So everything's a singularity, and everything's expanding, not exploding. People think that it's an explosion. It's not an explosion. It's an expansion. Now, as we know, the first law of thermodynamics says energy and matter cannot be created or destroyed, but it can change from one form to another. So, what happens during that Big Bang was everything was ridiculously hot. The first 1/100th of a second, it was over 100 billion Kelvin. So that's hot. Now, as we know, a lot of heat is basically comes from movement or energy. So this kind of expansion caused a lot of heat. So as that was starting to expand out, things started to slowly get cooler, and we have the building blocks to atoms are called photons. Photons are basically they're kind of what attracts protons and electrons and to help form that bond. Now, as things started to cool, we had photons, and then we started to see electrons slowly getting formed, and protons, neutrinos, antineutrinos, and things like that. So, as they're shooting out, eventually the photon's chilling, doing this thing, and all of a sudden the electron's here, and it kind of attracts that, and there's a proton, and they're doing that thing. Of course, this is the really layman, and I could be ruining this up, but this is the basic gist of what's going on. So, yeah, so then, as we know, hydrogen was one electron, one proton, and I just did a C, one electron, one proton, and that photon put those things together, and boom, helium. So since it was such a basic and light element, it formed rapidly as it started to cool down. So we had basically a whole lot of time and a whole lot of hydrogen gas. And then, of course, you need a lot of gravity. Now, we know that gravity is the curvature of space and time. And, as far as how it was formed, that's a little over my head. But we know it's there. And that's another question for another day. Because that's just a little beyond me. Maybe someone smarter than me can come up with that. But I'm not. So gravity, as we know, it's just basically, one mass pulling in another mass together or towards it or pushing it, as far as I think that's what Siddhartha was telling me. But still, basically, anyway, whatever. I'm just talking too much. So that helium was drawn together. I'm sorry, hydrogen. Hydrogen was drawn together. And when all that drawing together and that compression formed a lot of heat. A lot more heat. And once basically it gets, I believe, 1,000,000 Kelvin or just really, really hot, it starts a process called nuclear fusion. Then to make hydrogen into helium is called the hydrogen fusion process, and essentially you have 4 hydrogen protons, and of course it still has electrons and protons and all that stuff and all around it, neutrinos and what, but essentially they come together from all that heat and gravity and pressure and all that stuff to form into helium. Now, without going into too much detail, basically, stars have different forms, the red dwarf and white dwarf and all that stuff, the different phases they go through. And in those different phases, the core compresses in different ways, and there's different heat temperatures, and because of those different heats and pressures and different fusions are able to form, such as beryllium and carbon, and different elements like that. So I'm not going to go into too much detail, because you can just look that up. There's basically fusion from hydrogen to helium to all those different elements as they help form each other. But hydrogen is your base. So hydrogen, energy, compression, gravity, you just all starts a fusion process, and we have the different elements. Now, there's an important thing to know, is that the formation of the planets did not come from the Big Bang Theory. The Big Bang happened, over 14 billion years ago. The formation of our universe was about, or our galaxy, I'm sorry, was about 5 billion years ago, if I remember correctly. Long ago, but not as long as the Big Bang. The stars slowly started to, form, and more explosions, and we slowly started to see iron and all these different elements come about, and this iron turn into, rocks and meteorites. And again, I'm probably doing this an injustice, and somebody's probably going to pimp slap me with science, but so as those rocks started to form, the heavier metals and heavier materials started to form. They started bouncing around, and there's tons of rocks, and boom, 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 and then planets start to form. Meanwhile, they're kind of being affected by the star's gravity, and they're circling it, just like, rotation. But then something happens in the formation, and they get hit by a very big, huge rock, and it actually makes it spin the other direction. We see this with Venus, as it tilts on its side, and there's another planet that's kind of I think it's Jupiter, actually. It spins the other direction. Basically, that really big rock hit it, and boop, like a cue ball, or the ball just started spinning the other direction. But remember, gravity is doesn't really care if you're spinning in one direction. You're still going to go in one thing, in one way. But once that spin starts, you're going to be going that direction from now on. So long story short, something hit the planet, a really big rock hit it, probably close to the size of the Earth. And there's actually a big theory that the Earth at one point may have actually been spinning the other direction until it got hit by the moon, and now it's spinning in that same direction. Your next question, G-Man, was, have we ever seen stars form and provide video evidence of it? Well, even if we could provide video evidence for it, you would be literally watching it for millions of years. And I don't think you have the bandwidth for that. I've been in Hangouts with you. You don't have the bandwidth for crap. But, so what it is, it takes like like 100,000 years to get that proto, the very beginning stages of it, and then it takes millions of years to form afterwards. And even if we could watch it in its process, there is so much heat and so much dust and so much stuff going on that we can't even see it. We have been able to see what's called star nurseries, where we see them, the stars from very, 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 very young, and we can see their changes, and so we can basically work our way back and figure out what it was how their beginning was. So no, we have never seen it, and we never will unless anybody exists for millions of years, or we get a really cool camera and record it for millions of years, but still. Now, as we talked about earlier, with the formation of stars and how hydrogen was formed, how helium was formed, how at certain points we could, after make beryllium and then carbon, and after different phases of the stars, we have all the different elements that can be made. And again, I'm not going to go into great detail. It's pretty much already been covered, and you can look anything else up. Basically, there was, after the Earth was formed and become the planet, and there was rocks and everything. And to answer your question, G-Man, about the whole, if we were closer to the sun by a few inches or whatever, would we burn up? No, not even close. See, sun, Earth revolves around the sun, right? But it's not a perfect sphere, right? It is an elliptical, so it kind of comes out a little bit an elliptical shape. Now, during the summertime, we are 152 million kilometers away, right? During the winter, we are 147 million kilometers away. There is a 5 million kilometer difference. So there you go. That creationist argument, time to go bye-bye in general. Not just saying you, just in general. It's a terrible argument. In the early 50s, we had two scientists that had kind of proposed this idea of the Earth early atmosphere being created by hydrogen mostly, and then traces of oxygen, nitrogen, and carbon. Now, so this scientist saw these observations and said, well, okay, well, maybe, let's see if we can recreate it. So they made a little small area and introduced, hydrogen, oxygen, nitrogen, and carbon. And, very high amounts of hydrogen and very few traces of everything else. And he wanted to basically speed up the process, because it was supposed, Earth took a long, long dang time, and all these processes were really long, so he sped it up. So what he did was basically took something that did put out an electrical discharge and just kind of shocked everything. I don't know. I'm really Reader's Digest spitting this back out. But after about a week, he looked inside and he had noticed that the hydrogen had formed with oxygen to make water. The hydrogen also combined with the nitrogen to form carbon to make methane, and hydrogen atoms had combined with nitrogen to form ammonia. And then as he looked inside, he was digging around and seeing what was in there, he had found amino acids, which are the basic building blocks for proteins, and proteins are what forms the outsides of your cells. So we have life coming from non-life. That is fucking amazing. And of course, this can be recreated today, and we can verify this, and of course they used it, and then later DNA came involved and really changed things up as well, and finding out how important that was. But we literally have an example of life coming from non-life. Now, this is just an example. Is this exactly what happened? We're not sure. This is just a theory. There's actually another theory that's going right now, but basically it has something to do with volcanoes and material mats, or basically there's this bacteria and it's living next to this hydrothermal vent, from the vent from a volcano shooting out stuff. And that's just another different theory. And there's different stuff, but we do have a significant example of natural processes, and of course it was sped up from that electrical discharge, but life came from non-life. Now this one, I'm going to be lazy because this is way kind of out of my league, and I don't really feel like, trying to break this down myself. So I'm going to read, it's actually the wiki, if you want to look it up, it's just sexual space reproduction. It actually goes into the history, but I'm going to read it for you since you did ask for it. The evolution of sexual reproduction is a major puzzle. The first fossilized evidence of sexual reproduction in eukaryotes, which are these multi-celled kind of organisms, just tiny little just swimmer kind of things, is from the Stenian period, about 1 to 1.2 billion years ago. There are two main processes during sexual reproduction in eukaryotes: meiosis, which is involve having the number of chromosomes, and fertilization, involving the fusion of two gametes and the restoration of the original number of chromosomes. During meiosis, the chromosomes of each pair usually exchange genetic information to achieve homologous, is that a word? Homologous recombination. Evolutionary thought proposes several explanations for why sexual reproduction developed and why it is maintained. These reasons include fighting the accumulation of deleterious mutations, basically the mutations that are genetic mutations that change or disappear over time. They're useless mutations. Then increasing the rate of adaptation to the changing environment. And then there is what's called the Red Queen hypothesis. Basically, you're dealing with competition. There are species that co-evolve. So species A has claws that are really, really sharp. This is a terrible, terrible analogy. But species B, there was a genetic mutation that caused this species to have, or this variation of the species to have tougher skin. So, and these two battled it out for a long time. And so the ones that survived the scratching a little bit better, they tended to live longer and they survive. So then as this species had to start to evolve, because the ones that had that mutation, which it had sharper claws, were more likely to survive. And so then they started that. And there was just back and forth. Boom, 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 back and forth. This one got tougher skin, and this one had sharper claws. This one got tougher skin, and this one got sharper claws. And that started to cause as coevolution. And I lost my point. Or as an adaptation for repairing DNA damage and masking deleterious mutations. Yeah. So there's a few examples. Like I said, sexual reproduction in the wiki explains it pretty well. It goes into better detail, but hopefully that was enough to kind of answer your question. Basically, it's been happening for a long time. It was very basic, very generic, and I'm sure it was a good while before there were penises. But how that formed, I don't know. And again, I don't feel like going into that. But there's your starting point. That's where sex started. That was your question. Where did sex start? Pretty much there. All right, so we just covered about the whole how organisms, life came from non-life. Now we're going to have to fast forward a few million years, and thank you for not making me explain how we went from a simple amino acid all the way to a fish. So let's just start off from the fact that we have fish. Now, there was a certain type of fish after a long time, and this was called the ostracoderm, or ostracoderm actually. I'm not sure, but it was a fish that had a very bony structure, very heavy armor, thick bony plates and scales. This is actually this is probably, or most likely the vertebrate animal. Like, this is the first animal with a vertebrae or a spine, because of all that structure. Remember when I talked about that coevolution? That where, like, there was a certain species that one was attacking the other, and so it had to structure that. Well, actually, I had no idea that I was going to perfectly set me up into this into this question. So they had the fish called the Ostrostoderm, and it had a huge, like I said, spiny cover and protection. Meanwhile, there was two other predator fish. One was called the Encanthodians and the Placoderms, and the Placoderms were huge, giant fish, and the Encanthodians, they had really sharp jaws, and so again, coevolution. That sharp jaws was killing things, and so species, the Ostracoderms that had that sharper, a denser cover and that thicker bone, they survived better. So as time went along, they got really tough spines and tough back. And meanwhile, this fish, the one with the sharp jaw, started getting sharper teeth, blah blah blah. Now, eventually, the Ostracoderm had to try and continue to be stealthy because it could survive, but it wasn't good at attacking. Basically, imagine, kind of like just a turtle or something, or a porcupine. It had good defenses, but it wasn't much of an attacker. So it started to kind of lay low to the ground, right? Just doing its thing, trying to find food, but not piss off anybody, not get seen. Over time, it started to kind of get this mixture of a gill slash foot kind of bone structure over time, because it was using it to walk along, and that was good because it actually helped them be stealthy, because when fish are doing their thing here, they generate waves, and but when it's walking on water, walking on the sands, on the shore, whatever, on the ground, it's much quieter. So that species started to grow feet. Now, this was very basic, like proto feet. I mean, they were still kind of like flopping on land as they were going along, right? And then slowly after time, they kind of started to be more like real feet, or feet like that. Now, why were they walking out onto the land? Well, like I said, this was a species that was not the fighter type. It had strong, solid defenses, but it couldn't do much. It was trying to remain stealthy and keep away from these predators. Now, they were walking along, and then they were probably, one was probably chased by one, and he's like, boom, 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 I gotta go, get the hell out of here. He got up on land, and that fish couldn't get him. It's like, all right, this is not a bad idea. And so the kind of species that could actually make it out there, such as that Ostracoderm, started to walk out more onto the water. Sure, it was still floppy like a fish, but it was a good way to escape from prey. And as such, they started to survive more. And their numbers started to grow. And then they started to slowly evolve, and they started to get more feet, or more feet-like structures instead of fins. This is the current, or the common ancestor to amphibians. But what about the lungs? How did they learn to breathe? Because obviously that's still pretty hard because they have gills. Well, now we know there was different types of lungs that formed for different types of creatures. But as far as the fish were concerned, what happened was early on in their existence, there was basically a genetic mutation for a kind of a pouch that kind of formed inside the GI tract inside, and basically it was used for buoyancy control to kind of help them float and do the kind of when they're swimming and everything. But as that grew and changed, eventually another genetic mutation along those millions of years, or I don't know how long it was, that allowed or made it possible for that same pouch for oxygen and CO2 exchange, allow them to kind of breathe that air. And so more, as it kept going, eventually that sac became bigger and bigger and bigger, and then voila, you have lungs. So again, we have like this Ostracoderm that became the amphibian. So now he's got legs, or fin-like leg things, and now he's got a tract that actually allows him to breathe. So now he can be on land, and now he can be on water anytime that he needs to be. Now, probably for the most fun question is how did species evolve? You asked. How did it evolve from a non-cat? And now I believe just with this past example, I believe that's pretty much all of the explanation you need, but I'll back up. Like I said, we have the ostracoderm. Now, and it was that bony fish. It was that vertebrate fish. And slowly, because of survival tactics, walking on, the sand and slowly evolving, and then to where it had more feet-like structure, and then was slowly able to start breathing. And that's how we got the amphibians. So, that is an example of how creatures evolved. But here is one of the biggest struggles that I can see that you're going to have with this G-Man, and most creationists do, is that whole idea with transitional fossils. And now, if we were to look, let's go back to that ostracoderm. That was a pure fish, right? Straight up solid fish. Now, later on, one species later, it's got a tiny change in the fin structure, and this can walk more like a feet. Then another offspring, and it's just slightly more like a foot, and more, in every generation. This is a long time, and I know you know that. And slowly it became like feet, and the same thing with the lungs. Now, so again, it looked more like a lizard or an amphibian kind of creature, like not really a frog, but kind of an amphibian kind of creature. And so we have a process basically called taxonomy. It's a study of how we name things and why we give things characteristics. We may name things off characteristics, and I believe you even said this in your video. Where did it come from? The characteristics behind it, and I can't remember what they are for the life of me. But it's an entire study on why we name things the way we do, and I highly suggest you look into it. So let's just fast forward, and look at some fossils right now. Let's just imagine we found that ostracoderm fossil and that amphibian fossil. Now, if we were to take a fossil of that amphibian, that later named amphibian, I don't have the name for it, so I'm just going to call it the amphibian, and then that fish-like fossil, we would say, let's see, what, are they related? What is this? What is this? We don't know, so we start going, okay, do they have anything in common? Well, we can look at that amphibian and say, okay, this thing has a vertebrae. Okay, so that's something they have in common. Oh, this amphibian, it has a kind of foot-like fin thing. Well, this thing has fins. That's kind of something they have in common. And they go down the list. And they'll probably use DNA if that's possible. I don't know that much about DNA and how it can be extracted from fossils. It's whatever. But they categorize this, and then but it would be really hard to say, well, this obviously is a direct descendant from, this fish to this amphibian. It's hard to say this is a direct descendant because they have some characteristics, but it's way too early to call that. So, and then they keep digging and keep searching, and they go, oh, look, there's this fossil over here, and it looks more like this fish and a little less like this one. It has the same characteristics, but look, the sack's a little bit smaller, and the feet aren't so much like a fin, or a little more like a fin than they are feet. And then they keep digging, they keep looking, go, oh my god, look, here's another one, and this looks even more like it. This one has more fin-like and less feet and a smaller sack. And they keep finding fossils up to that point. And then they can go, oh, look, this most likely, according to this evidence, is this creature's transition from a fish to an amphibian. Now, of course, they're different species now, so they can't mate or anything. That's far beyond that point. On some slightly depressing news, after I was just about to finish uploading this, I had later found out that the ostracoderm is not the first true ancestor to the amphibian that I had been talking about. It was actually the Eogyrannus and the Ariops. These were the first true ancestors to the amphibians, but the point still remains the same. It is a very clear example of how things can evolve from one species to another. I mean, if that, the ostracoderm could have, easily become that amphibian, with a strong vertebrae, because it would have had the feet, It would have to be able to breathe air and stuff like that. It would have been a completely brand new species. So still works. Just I wanted to make sure I was more factually correct. Now, as far as how can they tell if a species can't, mate with another one, like if it's beyond that species, I don't know. I don't have a clue. I don't know if they probably have some kind of workaround or something. I don't know. I'll look it up. But I want to clarify, this is all based on observation. They aren't coming to a conclusion that, oh, this fish is obviously related to this vertebrate. They say, hey, look, these things have a lot in common. Let's see how much they have in common, and then we can make our observation or our findings based on that. So, there you have it, G-Man. That is how a species can evolve from one thing to another. Now, I really don't want to try and guide you all the way from one species all the way to the primates to where we are as humans. I am not Aaron Ra. I don't have that kind of evolutionary background and can provide evidence or anything like that. But hopefully, and I want you to let me know if I really have, and I can probably clarify it or re-explain it. Hopefully I was able to let you understand that is how species evolve from one species to another. Now, in the final thing I want to talk about, I want to drive this point home about micro and macro evolution. This is the bane of my existence when I try to talk about evolution with people. I hope you understand from what you did learn is that the difference between microevolution and macroevolution is time. Macroevolution is a term that was made up by creationists. So, for example, let's go back to the ostracoderm and then the possible future amphibian. Now, as I said earlier, I found out it wasn't the true ancestor of the amphibian, but it still is. It's a possibility. If this species actually had gone extinct for one reason or another, if it hadn't, it would have formed a brand new type of amphibian kind of species, or maybe different species altogether. I don't know, but let's just kind of pretend that this species had continued to exist and continued to evolve. I don't know even how far it went actually past it before it went extinct. I don't know how far it reached, but let's just make up a species here. So we had the ostracoderm, that was the invertebrate fish, the vertebrate fish, sorry, and then it became this new species, but for now we'll just call it the amphibian. So it was an amphibious species. For the purposes of this example, I'm just going to say we're going to start off with the ostracoderm, and then we're going to have species X. He is an amphibian that has no fins, feet. It has full-on feet. It fully breathes, with lungs, but it also can go underwater, just like any other amphibian. And he has a really long tail. Now, when a creationist looks at these, or when a scientist say, we look at these things and we can say, hey, look, we have this is species X here, right? And then we found this fossil where, we don't have doesn't have really a long tail, but we see that there's a lung is starting to form here. And we see that it has feet/fin-like characteristics, but we see it has a lot in common with this ostracoderm because it's a vertebrate, and it even kind of has the same point in the face, or something like that, and it eats the same foods, and it eats all that, so it has a lot in common. So scientists can look at that and go, well, it's most likely that this fossil that we found here in the middle between species X and this ostracoderm, this is a transitional fossil from species X to here, because there are no other species that we can find, and this has way too many characteristics that look like this. However, a creationist will go, well, look, there's way too many gaps in between here. This isn't a species. This isn't a transitional fossil. This is not macroevolution like you talked about. So then we find another fossil, and it's closer to this guy. And you're like, oh look, oh this is the one here that's a longer tail, and it's got bigger lungs, and it looks more like species X. The creation's like, oh no, it's because you still have the long way to go from here. And then we find another fossil here, and it has no tail, but it's starting to have more feet-like structures, and it's eating the same food. It has more characteristics. And they're still upset, and they're still saying that that's not full on, that's not macro. That looks like macroevolution to me. That's not microevolution. The only way that a creationist would be satisfied to say about microevolution is if we had a transitional fossil from every offspring from that fish creature all the way hundreds of thousands to millions of years later until we got to species X. But we don't have that luxury of having that many fossils. A transitional fossil is not a perfect jump from one fossil to the other. It's just saying that there are enough characteristics to call this a change in species. To say, look, there is nothing else similar to this. There is nothing else even close to the same characteristics. So when we can study the DNA, we can study the characteristics, we can study what it ate, we can study where it originated and the environment that it lived in, and can, with these observations, say this most likely is that species evolved into this new species. And I actually have to take back what I said, because we actually do have several examples of basically a speciation changing from one species to the next. We actually do this with plants, and I can list these down below, and I'll probably add that to the video later. But for one example, it's called the Madeira house mouse. Basically, after a fire of some kind, or a colonization of the island Madeira in the 1400s, 6 distinct species of mice evolved from that one type of mice. That is just one example, and I'll list that in below. But we actually do have many. I think we did some with some others. Darwin's finches, of course. Actually, there's some people that after Darwin left, and of course way later, I should say, they continue to study the finches, and you continue to see the changes that occurred. We have all kinds of examples, actually. So even though macroevolution is just a word or a phrase that creation is made up, we actually do have enough evidence to actually show that we can make it happen. We actually do that on a regular basis. Honestly, if you go to answersingenesis.org, there is a section called Arguments that Creationists Should Not Use. The microevolution, macroevolution argument is like number 2 or number 3. Answersingenesis.org, the creationist people are telling you to not use that argument anymore. If you don't believe me, then please trust Answers in Genesis, and I never thought I would ever say that. So I'm done. This has been really fun. I really hope that I was able to help you out, G-Man. Now, I want you to understand, I'm not trying to deconvert you or anything. And this may have not done that, and most likely not. But you have to understand, there are Christians that believe in evolution. There is nothing evil about evolution. There's nothing sinful about evolution. I mean, was it 30%, I believe, of Christians believe in evolution? They believe that God guided it. And of course, I disagree with that. But they agree that evolution is possible, and evolution can explain why we have the human species. And maybe this helped you out. I really hope it does. Seriously. I hope to hear your response. But thanks so much for this. This was really fun. And peace out.